So in this video, we'll briefly introduce how to compute the slope of a point along a parametric curve. So for example, if we have this parametric curve and we want to calculate this tangent line to a point along the curve, well, there's a couple things we need. And we can use our friend down below, the point slope formula of a line, and basically try to fill in the necessary information we need to find that tangent line. So if we're given the point along the curve, say at x0, y0, this is again just some point like 2, 5 or something along that curve, we would just plug in the x and y values accordingly in that point slope formula. The last thing we need though is the slope of that tangent line, or the slope along the curve at that particular point. And for us, in terms of parametric curves, the slope for us is still how we think about slope from calculus A. We still think about slope as a rise over run type idea. So if you remember this, what this really boiled down to us was basically a change in y over change in x. And for us using parametric curves, we can think about this actually very much the same. We still care about a slope, and since we're in calculus, we're thinking about this as sort of, an instantaneous kind of quantity. So instead of thinking about some discrete change in y over change in x, calculus gives us the power again to think about these as instantaneous kind of properties of a function, dy over dx, our derivative. But remember, kind of the tricky thing here is we don't have a function, y is a function of x, so we can't just take the derivative of something. We're given this parametric curve where our individual coordinate functions, both x and y, are themselves some function of this other parameter t. So I still want us to think about slope as a change in y over change in x. And it turns out that we could do a lot of chain rule operation stuff, but the slope formula actually boils down to something a little more intuitive. We would just take the derivative of our y coordinate function with respect to t, and we divide it by the derivative of our x coordinate function with respect to t, and that'll actually give us a method to compute the slope of a parametric curve at a particular point. Now, I want to draw our attention to something before we go on to this next problem of actually computing a tangent line. This right-hand side, after we do this ratio, this is going to be a function of that parameter t. Which means this quantity, even though we have a dy over dx, this is still a function of t when we're thinking about parametric curves. So I just want us to be aware of this notation, dy dx really represents a slope because again, it's the same idea for a slope as before. How much do we change in the vertical direction versus how much do we change in the horizontal direction? So we're still thinking about this dy dx type slope quantity, except our function y is not directly a function of x for parametric curves. All right, so let's go on and actually compute a tangent line to a parametric curve. So we're interested in computing this tangent line to the curve that we're given below. X is equal to 5 minus t squared, and y is equal to 2 sine of t minus t. And we're interested in evaluating this curve when t equals pi over 2. So if you remember from earlier, just a little bit above, we have our point slope formula for a line, and we need to just try and fill in those quantities accordingly. So our point slope form of a line, if we're trying to write this tangent line, is y minus y0 equals m times x minus x0. And there's a couple unknowns right away. We don't know what y0 is, we don't know what the slope m is, and we don't know what the x0 point is. So what do we have in this problem that can help us fill in these details? Well, we have the curve itself, of course, that we're given, and we're also given a specific point along that curve or a specific parameter value that will give us a point along that curve, maybe I should say, t equals pi over 2. So the first thing we could actually try to do is compute both x0 and y0. And the way we can compute these is simply evaluating our functions or our parametric curve themselves at t equals pi over 2. So first, let's find x0, y0. Again, this is the point along the curve that we're actually computing that tangent line. So the way in which we do this, we take our x function and we'll just evaluate it at pi over 2. We'll take our y function and we'll also evaluate that at pi over 2. Because again, that is the t value that we're interested in computing this tangent line for. So x is equal to 5 minus, well, I guess pi over 2 squared, which this is just going to be something messy. This is just equal to 5 minus pi squared over 4. Whatever that number is, that is our x value. Y is equal to 2 times sine of pi over 2 minus pi over 2. All right, so sine of pi over 2, this is one of those trig values that's popular to know. Sine of pi over 2, that's actually just equal to 1. So we have 2 times 1 or 2. So this y value is actually equal to 2 minus pi over 2. So we actually know what these points x0 and y0 are. x0 is just equal to 5 minus pi squared over 4. And y0 is equal to 2 minus pi over 2. So we know what those values are. The next thing we need to figure out then is that m value, or what the slope will be for our parametric curve. So let's go ahead and try to find that. And remember, from up above, we have that our slope, even when we're thinking about parametric curves, is still a change in y over change in x, or in our derivative or our calculus notation, dy dx, although this will still be a function of that parameter, in this case, t. And the way we compute this is by taking dy dt over dx dt. So let's compute those derivatives. So if we compute the derivative first of dy dt, taking a look at the function for y up above, that derivative will give us a 2 times cosine minus 1. And now if we take a derivative of the x equation, again, now we're looking at dx dt for that denominator. Taking a derivative of the x equation up above will just give us a minus 2t. So in that denominator, we have minus 2 times t. And how do we actually compute the slope? Well, we know what the slope formula is. Remember, we have the slope m equals dy dx, which was the derivative of y divided by derivative of x, both those derivatives with respect to that parameter. This was equal to 2 cosine of t minus 1 all over minus 2t. And I just want to bring out or make the point that we do see that this derivative is a function of that parameter t. We don't see any y's, we don't see any x's anywhere. This is a function of that parameter t. So this dy dx notation, it's just important that we know what this represents. All right, and the last thing we would need to do here as well, if we're interested in this slope at a particular point, we need to evaluate this point, or this slope, excuse me, at the t value associated with that point, which in this case is pi over 2. So if we just plug in pi over 2 for all the t's, we had 2 cosine of pi over 2 minus 1 in the numerator. And in that denominator, we get minus 2 times pi over 2, which we could reduce to the following. Cosine of pi over 2, well, that thing's equal to 0. So in that numerator, we get a minus 1. In that denominator, we get a minus pi. So the slope is actually at this point is actually equal to 1 over pi. So let's fill in all of these details we just found for the slope, for the values of y0 and x0, all into our point slope form of that line. So just so we're on the same page, let's make sure we know what we're substituting and why. So we evaluated our parametric curves at the point t, or the parameter t value, associated with the particular point we're looking for. And we found that y0 was equal to 2 minus pi over 2. And we found that x0, or the point x coordinate value along our curve, was 5 minus pi squared over 4. And the last thing we just saw was we found the slope value was 1 over pi. So for that m value, we're going to substitute a 1 over pi. So our point slope form of our line is equal to y minus the quantity, 2 minus pi over 2. And this is equal to the slope, 1 over pi, times x minus the x value at that point along the parametric curve, which in this case is 5 minus pi squared over 4. And that would be the point slope form, or the equation of our tangent line at that point t equals pi over 2 along that parametric curve we were given.